So this is a cross-cutting phenomenon that both draws on and contributes to all the four Skeeks topics that Roger mentioned yesterday. So it's key to the origin and evolution of neutron star magnetic fields, the effects of accretion and merger, the coupling of neutron star surfaces and interiors to the magnetosphere. I'll be talking primarily about magnetic fields in disks and jets. So just for the background, it's hard to imagine that the raw material for an accretion flow is not magnetized. If it were not magnetized, that would be harder to explain than that it is being magnetized. And it's acted on by the kind of traditional forces we think of in disks: rotational shear, gravitational buoyancy. There are instabilities like magnetorotational instability that's been mentioned many times, maybe magnetic buoyancy instabilities like Parker. And the structure of the field influences how magnetic energy is dissipated, how a corona is formed, how jets are launched, and the nature of accretion, the flares, the bursts, and the collimation of the outflows. So just having a magnetic field is not enough. We have to ask in detail how it becomes configured. So I'll be talking primarily about work being done at CETA, at Columbia, at Maryland, and Princeton, and also Wisconsin. I am not going to be talking about the work on neutron stars that Yuri gave an exciting talk about. I guess it was the first talk in the morning after Roger. So I'm not going to talk about that stuff. I'm not going to talk about magnetars. I'm going to kind of talk about dynamo basics. But I did just want to mention a few of what I see as the major achievements by Skeeks in the last 2.5 years. So there was the discovery and analysis of a large-scale polarity reversing dynamo driven by MHD shear flow instability, and the development of a mean field theory that can, we think, be used so that you don't have to do the detailed simulations yourself. There was a demonstration through GRMHD simulations that if you start with an initially toroidal field in a disk, loops of magnetic flux erupt, a poloidal field is generated, and a striped jet is launched. And then there was complementary work showing that if you have a disk with an initially poloidal field, it can grow a corona. You don't have to put the corona in, it grows. And the details of how the magnetic field is configured near the object have profound consequences for how the field evolves and what the accretion flow is like. And a lot of this was enabled by the development of really a first principles prescription for magnetic reconnection in relativistic collisionless plasma. This has already been alluded to several times, so I won't be the first one to talk about it, but it is a cross-cutting achievement in itself that impacts many aspects of what we do. So these are the main things that I will talk about. Okay, so first I'd like to convince you that this is a really hard problem that has had a lot of staying power and is not completely solved by any means. And then I'll talk about what's been accomplished at Skeeks. I'll go over a little bit this reconnection prescription, the shear flow dynamo, and the growth of poloidal from toroidal field, and the growth of a corona from an initially poloidal field in a magnetically arrested disk. And then I'll just say a few words about what I personally am most excited about, which is to take that shear flow dynamo, follow the energy in a kind of Skeeks relevant plasma model. That will become more clear in the next few minutes. Okay. So dynamo studies have a long heritage. There are two very well observed dynamos in the solar system. There's the geodynamo, which is irregular, has a long time scale. And there's the solar dynamo, which is very regular. This is famous butterfly diagram showing the appearance and disappearance of sunspots at intermediate latitudes, migration down toward the equator, disappearance and resurgence. And of course, in the pulsar community, the periodicity of this doesn't really impress anybody, but by normal astronomical standards, it's very impressive. And this was the sort of first impediment to understanding the solar dynamo was the so-called Cowling theorem, which says that an axisymmetric magnetic field cannot sustain itself against decay. This is actually violated in general relativity, but I don't know if it's had any impact. So the main ingredients of the dynamo were first isolated by Eugene Parker back in the 50s. The key ingredients are small-scale turbulence and some kind of large-scale rotation or shear. And if you describe their effects by a couple of parameters and turn the knobs, you can reproduce the solar cycle. And this was done for many years. But for various reasons, we need to go beyond and really kind of find some more fundamental understanding that's also compliant with the conditions of the medium that we encounter in skeeks, in extreme electrodynamics. So, sorry, there are going to be a lot of equations here. So I'm just going to do this in MHD. We have kind of non-relativistic MHD. We have Faraday's law. And the electric field is the motional electric field so this is induction of mean magnetic field by a mean flow. And then the effect of the small-scale motions is conventionally described in terms of these two parameters, the so-called alpha effect, which measures the effect of small-scale helical turbulence, and the beta effect, which is thought to induce a diffusion of the mean magnetic field. So fluctuating flow and fluctuating field are subsumed into these alpha and beta coefficients. And the alpha and beta are generally tuned up and down to get an agreement with the system in question. This has been applied to stars, galaxies, et cetera. Okay, so how could this, if we drill down a little bit, how could this work? So this is the famous Zeldovich stretch, twist, fold paradigm for what a dynamo has to do. So the idea is that we start with some loops of magnetic field. We stretch them, becoming stronger. Then we twist them. So you have to do something in 3 dimensions to twist it. Then we take the twisted loops and we fold them over each other. And then there has to be some kind of snipping process that builds in irreversibility here so that this cycle cannot go backwards. We're left with a field that's stronger than the one we started with. So that's the Zeldovich stretch, twist, fold paradigm. And I've kind of taken this, I've kind of annotated it to show you where the field would have to be snipped to get these two loops now to line up in a way that reinforces them instead of canceling them. So in addition to this, there's typically some kind of large-scale shear that imparts a dominant orientation. So for a disk, this would be poloidal or toroidal. The details of how this reconnection works are important for understanding plasma heating, driving dynamics. So a lot of free energy can be released in this process for macroscopic phenomena, and also particle acceleration. So we've already heard a little bit about that through various talks the last couple days. Okay. So why is this such a hard problem? Well, if we have a relatively fixed volume of field of plasma, and we want to increase the magnetic field, the way to do that is to lengthen the lines. So go from this cylinder to this cylinder. So to really build up the field by a large factor in a finite volume, you have to, you really have to distort them. So this is just an image of MHD turbulence by Alicia Galishnikova and other people here. I think Sasha was involved in this, Elliot, from a few years ago. And it shows that the magnetic field assumes a highly folded configuration. Okay, so not simple at all, highly folded. Okay, so how do you generate a large-scale field in a constant volume, stretching the lines, but not complexifying the field in this way that was just showed? This is a particularly acute problem in diffuse plasmas that have a large magnetic Prandtl number, that are much more resistive than they are resistive. And what typically happens is that you get some kind of magnetic spectrum that looks like this. It's peaked, so most of magnetic power is at a relatively small scale. This is a progression in magnetic Prandtl number going from 25 to 500, and you can see that as the Prandtl number increases, so it could be 10 to the 5 in a typical diffuse hot plasma, you move to, the peak moves to smaller and smaller scales. And so this is an old plot by Alex Shekachian, but it remains sort of as flagrantly problematic as it did 20 years ago. Okay, so we have to find some way of simplifying the field, and that way is magnetic reconnection. So how does that work? So I'm just going to go through this briefly. So I've drawn here a current sheet. This is kind of the early idea of magnetic reconnection due to Gene Parker and somebody named Sweet. And the idea is that you bring plasma in at some velocity over this whole broad current sheet, and then you have to expel it through a region which is very thin. And it's very thin because in a highly conducting plasma, the only way currents can dissipate is if the scale of this reversal here is very small. And if you go through a couple of continuity requirements, you find that the ratio of this inflow velocity to the alphane speed is proportional to the resistivity divided by the macroscopic length of the current sheet times the alphane velocity. So this type of configuration leads to very slow reconnection. Now, yesterday, Anatoly showed something that looked more like this. So instead of a long, thin sheet, there was a broad X. So here's the diffusion region, just kind of drawn here like a black box. Material is now brought in and expelled through these broad channels. So you can just see, based on kind of mass conservation arguments, that this is going to be a lot faster than this. This is the so-called Petschek flow that Anatoly alluded to. So what will take you from this to this? Well, there's an instability that breaks up this current layer. It's called the plasmoid instability. It was the PhD thesis of Nuno Loureiro, who died so tragically a couple of months ago. Another thing that will do it is the local enhancement of resistivity. And the discovery of the Columbia and CETA groups that is having a big impact is the discovery through PIC simulations that the charge can become starved in regions of these X points, which acts like a locally enhanced resistivity and is being modeled as such. Okay, so now these very classy slides are due to Lorenzo, and I'll just take you through it briefly. So in the co-moving frame, the electric field, the current, and the resistivity are proportional in this way. Faraday's law in the charge-starved regime, Ampere's law reduces to this. So the current, how big can the current be? Well, it cannot be any bigger than the electric charge, the number density of charge carriers, and the speed of light. it just cannot be any bigger. So the criterion for applying this charge-starved prescription is that there be a non-ideal electric field. So the ideal electric field is the one that you have when you go to the observer's frame. And it can be manipulated into this form. So now we have the sort of relativistic versions of the Ohm's law. Here's a reference. And here are some tests kind of for how it works. So the idea is to apply this as a subgrid prescription that's validated by PIC simulations. It's applied when there's a non-ideal electric field and there's an X point, and it works. It works quite well. I think these images were shown before. So what would be the next steps in something like this? So it's been tried in sort of relatively clean tests, the so-called Harris sheet. That was what you saw a moment ago. Here, it's also been tried for balding black holes, simple situations. What happens if you have a turbulent medium where conceivably you have lots of X points? How well will it work? This is just an image of some current sheets in so-called reduced MHD turbulence, where there's a strong guide field based, I think, on Vladimir Zhdankin's thesis or pre-thesis work. Just a good picture. The next steps are to incorporate this into MHD models, to include radiative cooling. So there's a nice poster that I encourage you all to look at by Savelli, student at CETA. Can we take this further? Can we include the signatures of plasma heating and particle acceleration into our subgrid model, come up with how these things would work in a disk, and apply them to models of shear flow turbulence, which is kind of dear to my heart, as you'll see in the next few slides. Okay. But I want to make one more point about reconnection, which is that it can occur outside the host system. So this is a sketch of what it might look like. Here might be the interior of a star, so these loops of field. And now I've just taken the twist, fold, and snip picture and turned it on its side using the miracle of PowerPoint. And now you can see that the magnetic reconnection will occur outside the star in the magnetosphere, in this case. What this does is it ejects so-called magnetic helicity from the system. So magnetic helicity basically describes the linkage of magnetic flux loops. I've just kind of sketched it here. In a non-resistive medium, a so-called ideal medium, it'll be conserved. But if we think of it as twist, I just can't help but think about these giant Hall waves that were discussed in Yuri's talk, this nice work by Ashley Bransgrove. The ejection of magnetic helicity is actually implicated in the solar dynamo, some models of the solar dynamo, and maybe it plays some role in maybe it's a way of feeding back magnetospheric activity onto the structure of magnetic fields in crusts. It is, at this point, just a thought. Okay, so that's it for the basic physical processes. So now I'd like to talk about the shear flow dynamo. This was Bindesh Tripaঠি's thesis work. He has a poster on it that goes into more detail than I will. So there was some discussion, particularly on the first day, of the role of sort of bringing in outside expertise to what we do at Skeeks. And this was very much, in fact, he was, I feel, the real expert, my colleague Paul Terry at the University of Wisconsin, who's a turbulence theorist. His background is in magnetic fusion. That's most of what he does. And we applied his methods and his ideas to this work, and it turned out to be very fruitful. And I think we should be doing this kind of thing with people from different fields. We should be doing this constantly. Okay. So here's the basic idea of how it might work. So we have a shear flow. If it's subsonic and superalfvénic, it'll be unstable to sort of Kelvin-Helmholtz type instabilities, and they grow vortices. So this is just a realization of turbulent vortices in a shear flow. This is from a recently submitted paper. It's actually on particle acceleration, but we used the shear flow instabilities as a model of turbulence. So you can see this is kind of an early stage, and then later on, this kind of secondary magnetic forces and hydrodynamic forces in this flow create a very turbulent structure, like so. So the turbulence remains confined to thin layers, but it's strong and it's there. Okay. So I want to say a little bit about turbulence driven by instability. So it's the most common way of studying turbulence is to just take a box and stir it, apply some force, and usually at a large scale, and then we get a cascade down to small scales. Turbulence driven by instability can be kind of different, and what we found in this particular case, so the kind of canonical picture of instability-driven turbulence would be, so you make some kind of large scale, you have some kind of large scale instability, and as it grows, there's kind of a nonlinear interaction of the unstable mode with itself, and it creates something at smaller scales, and then those smaller scales progressively through nonlinear interactions cascade down to larger scales. What seems to happen in this case, not necessarily every case, is that there's a stable mode which is actually very close to the unstable mode in structure. I don't know if anybody here remembers their Chandrasekhar, but most people learn about shear flow instabilities through this simple vortex sheet problem. And if you traced it through yourself, you might remember that the dispersion relation is a quadratic equation, and there's an exponentially growing root, and there's a damped root. Okay, well, what happens in that damped root? Turns out that this stable mode at large scales is pumped nonlinearly by the unstable mode. So in addition to driving small-scale modes, the unstable mode drives a stable large-scale mode. And this has the effect of kind of sequestering magnetic energy at the large scale. So it takes a bite out of the cascade, and it keeps some of the power at large scales. This, so we immediately thought about dynamos when we saw this. Here's an image of kind of how it works. So Bindesh was able to remove the stable mode. Okay, so this is at a time of 6, you can see the stable and the unstable mode. So you can see the rates of energy transfer between the two. You can see they just kind of go up and down. They're like mirror images of each other. It's very striking in this particular case. So we start with this initial turbulent condition. Then we take away the stable mode. And it turns out that the stable mode was canceling a lot of small-scale structure. And if we just let it evolve for a very short time, the structure becomes even more complex. And whereas if we had kept that stable mode, we just would have gone from here to here. So the stable mode is really doing a lot to suppress the growth of small-scale structure. Okay, so this was pretty provocative, but what I'm showing you so far is in 2 dimensions, and we know that dynamos are inherently 3-dimensional. So we went into 3 dimensions. Now, people when people study the Kelvin-Helmholtz instability, they usually kind of console themselves with Squires' theorem, which says that the fastest growing modes are two-dimensional. So let's just stick with those. But there are unstable three-dimensional modes, and they turn out to have a very important effect, which is necessary for the operation of a dynamo. So let me show you the central result first. The central result, so we made this three-dimensional flow in unstable shear flow, starting from something very simple. If we measure the time in units of the kind of mean velocity divided by the layer width, the shear flow is continuously driven by an operator, a fictitious force, which prevents it from relaxing. And if we average over the domain and get the horizontal magnetic field, we started with a weak initial field that was uniform and in one direction, and we get this bipolar field, so one polarity here, one polarity there, that reverses not exactly periodically, but on a kind of characteristic time scale that I have to admit we never completely figured out what creates that time. This field has a large in-plane component and also a significant out-of-plane component. We did this just using resistive viscous MHD. Okay, so not as Skeek's plasma. That's why we'd like to take this further. And here's the magnetic spectrum. So in contrast to that peaked spectrum that is what you normally get in a highly conducting medium, most of the energy really is at large scales here. The field builds up to a sizable fraction of equipartition, and most of the energy is at large scales. So the dynamo, so don't be intimidated by this life cycle, this 10-step life cycle. I'm not going to go through the whole thing in detail, but I want to make the point that we would not get this shear flow dynamo without the generation of a secondary flow, these so-called zonal jets that are parallel to the initial shear flow, aligned with it, displaced from it, and have a three-dimensional structure. These zonal jets are key for generating and amplifying this reversing mean field. So here is just a little bit of that 10-step life cycle. So as I said, the shear flow is continuously driven by this relaxation operator. The initial magnetic field is quite weak. The initial alphane Mach number is 30. So the ratio of the alphane speed to the flow speed is 1/30. First, the Kelvin-Helmholtz instability forms these 2D vortex tubes, consistent with Squires' theorem, but then they make these 3D rolls. And then the rolls are kind of sheared out into jets that are invariant in that initial flow direction, the x direction, and they do a lot to shear the magnetic field. So we couldn't do this without 3 dimensions and without the generation of this secondary flow. And this is just a little more to show that it's the nonlinear energy transfer from the zonal jets that's really feeding the growth of that mean field. So this is a recently submitted paper, I guess under review. Okay, so I'd like to say a little bit on numerical methods. Those of you who know me did not expect this, but because we use kind of different methods than anything that's been discussed so far, I want to say a little bit about what we did. So these calculations are done with a spectral, in one case, a pseudospectral code in another. We started with the Daedalus code that was developed to a great extent at the CCA by Keaton Burns and other collaborators. But we switched at some point to the ghost code, basically because we wanted to apply periodic boundary conditions. We wanted something faster where we could do really high resolution simulations. Bindesh can give you numbers. In one case, a single hyperbolic tangent profile. In another case, a double tangent profile. And because we had spectral information, it was much easier than it would be in, say, a grid code to project, to do an eigenmode decomposition and project. Do you have a question, or just raising your arm?
No, we were just
okay.
Discussing the difference between fully periodic and conducting
Okay. Yeah. So we were haunted continuously by, sort of how the vertical boundary conditions might be affecting what was going on. Okay. So it turned out that this eigenmode decomposition was very useful even when the amplitude was highly nonlinear. So we projected things onto stable modes, unstable modes, and continuum modes, which are kind of localized, very localized spatially. They turned out not to do very much, contrary to my expectations. And so we were able to really kind of drill down and assess how different wave numbers contributed. Stable and unstable wave numbers contributed to what we were seeing. And this was also useful when we wanted to kind of start making a bridge to some kind of subgrid prescription and test some kind of low-order model. So how many modes do we need to retain to describe what's really going on? It turns out not that many. So eventually, we were able to make contact with a sort of relatively recent addition to the parameterized mean field theory, and that's the so-called upsilon coefficient. So I learned a new Greek letter in doing this work. Here's the upsilon term, and the upsilon term. So the ingredients of the upsilon term, here are actual representations for the alpha coefficient, the beta coefficient that I introduced before, and the upsilon coefficient. This quantity here is called the cross helicity. Tau is the kind of characteristic correlation time for the turbulence. If you have an alpha dynamo, it turns out to be kind of saturated by what's called alphanization, which is the alignment of the fluctuating magnetic field and the fluctuating flow. They're aligned, actually, in an alphane wave, and this happens over time in attempts to simulate the alpha effect. But this is exactly what the cross-helicity dynamo needs. The upsilon coefficient is actually proportional to U dot B, and I'm now going to use the power of the eigenmode decomposition. Oops, I thought I had that in there. No, I don't. But I do have a figure, or there's a figure in one of Bindesh's paper, and maybe on his poster, which I encourage you all to go see, of kind of demonstrating that upsilon is much bigger than alpha. Okay, so what are the next steps? Well, so this is very idealized. This is just a box full of dynamo. So the obvious question is, will this shear flow dynamo or some kind of close analog actually work in a disk? So a possible candidate to provide free energy through instability would be the MRI. We'll have to take stratification into account. Will it be friend or foe? Will it help the dynamo or wipe it out? And if we replace the fluid model with a viscosity and a resistivity with something that's more appropriate for a relativistic collisionless plasma, what will happen? Will it still work? So yeah, we don't know. But Bindesh is actually not doing a disk dynamo problem. He's doing dynamo amplification at the shear layer of a neutron star merger, which is something that's actually a lot closer to the original shear flow dynamo, and he's working on this with Andre, our new PI, one of our two new PIs. Okay, so now where might this all be going? So now I'm going to jump over the dynamo step and talk about magnetic field evolution in disks. And so a couple of central questions for this are, does the orientation of the initial magnetic field matter for the long-time evolution? And some ways in which it might matter are the formation of coronae, the launching of outflows, and the nature of accretion. So let's start with the case that you have an in-plane, you start with an in-plane toroidal magnetic field. So this is work that's led from Maryland by Sasha Filipov. It's a GR-MHD simulation. This is deservedly called a butterfly diagram. So this is at one particular location in the disk. This is at 21 RG. Time is measured in units of inverse Keplerian time. This is the toroidal magnetic field. This is the poloidal magnetic field. This is the original disk plane. And here in polar coordinates is essentially the latitude. And these are the two polarities of the initial field. Okay. After some time, it looks quite different. A poloidal field has formed and a jet has been launched. And because of the mix, so if you take a toroidal field going around like so, and then some loops pop out, so the field is going one way on the upward leg of the loop and then downward on the downward length of the loop, and then you twist that whole thing into a jet, it'll be a striped jet. And that's basically what it is. So the loops may be popping out as a result of a sort of buoyancy or Parker-like phenomenon. But things are quite different. The magnetic field scale is the same. We still have this polarity that changes over time. Reversals are pretty sharp. We don't yet have a theoretical explanation for this, and we don't have sort of a detailed explanation of the relationship between the poloidal field and the launching of the jet. And these are all things that we think will come. But so Sasha did produce this at some ungodly hour of the night in response to a wish list from me. So I'm going to show you two versions of the magnetic power spectrum. So this is as a function of azimuthal mode number. So this is basically a measure of how axisymmetric the field is. So these are not normalized with respect to one another. They're kind of self-normalized. I'll show you also a plot which you can track the growth of the magnetic field. This is the earliest time. This is the latest time. And you can see that initially the power is concentrated at a relatively high mode number, kind of in the 20s. But this peak shifts as we go from 450 R over C to 4,000 R over C. It shifts. More and more power accumulates at the large scales. And this smallest mode numbers is 0 to 4. Okay, so there's a clear progression in the axisymmetricness of the magnetic field. There's also a growth of the field. So these are the earliest, and this is the power, and all normalized in the same way, but code units, unfortunately, earliest to latest. So there's a significant growth of the magnetic field. Okay, what about if we start with something completely different? What about if we start with a uniform poloidal field in a jet? So here's work that's led at CETA but everybody's collaborating. And what's one of the, I think, remarkable features of this work is that it grew its own corona. So this is a GR-MHD simulation. Magnetic reconnection is numerical. It's not handled with a particular model, but obvious next step is to implement this new resistivity prescription. You have this large-scale field, large-scale colloidal field, and the corona has formed. So I think the kind of generic mechanism for forming a corona is if you keep dissipating energy in a medium that's gravitationally stratified, as you go to a more dilute plasma, the cooling times will be longer, and at some point the deposition of energy will outstrip the rate at which it's lost to radiation and other processes, and the thing will just puff up. And that's what we see here. So this is a zoom in. This red box is a zoom in shown here in more detail. And you can see this kind of thin, irregular, disky accretion flow here, and then the puffed up disk at the outer edge. And here's this beautiful realization of magnetic flux tubes, this twisted magnetic field. I think you're invited, when you look at these magnetic field lines, to think of the old Blanford and Payne, the launching of a flow, the kind of bead on a wire. One of the effects of starting with this thin disk here is that the current sheet has just kind of kept on going. It hasn't been disrupted, and it's the dissipation from that kind of continuously replenished current sheet that is feeding the corona. So two very different initial conditions, both leading to jets, outflows, and accretion. There's a long time evolution that's mediated by this. The truncation radius of the disk is slowly increasing. One of the other kind of unique features of this simulation is that they ran it for a very long time. I think it was 200,000 orbital times. So that's kind of a lesson if you want to do a quick and dirty simulation, things you just don't see unless you run it for anything approaching a reasonable time scale. They made a power spectrum too. This is work by Brendan Gale. And in both this and the power spectrum that I showed that Sasha made, we have power spectra now. So these GR-MHD simulations are sufficiently highly resolved that you can actually look at the magnetic power spectrum. In this case, at the scale at which the Rayleigh-Taylor instability is operating and the magnetic field is reconnecting. So it's really possible now to probe the nature of turbulence on these small scales. So I think we're just compelled to keep going on this. I'd like to eventually come to a kind of an integrated model of a dynamo in a disk, follow the dissipation of energy into different channels, into flow, into particle heating, into acceleration. How is it apportioned between the electrons and the ions? It's only through doing something like this that we can really track the development of a corona and any non-thermal particle population that's induced. And this will have implications for whether we form a striped jet or one which is axisymmetric and smooth. It'll have implications for angular momentum transport. I think that we've developed enough of the tools, and there are important tools out there in the community. Skeeks is not doing everything, just doing a lot. There are tools out there that will enable us to solve this problem, I think, in the next few years. So this is what I'd like to leave you with. These dynamo problems, these magnetic field evolution problems, they have a big footprint. They impact so many things. And we're living in a time when new theoretical methods, new computational methods, and observational discoveries are, kind of fueling a rapid pace of discovery. So we just have to keep going. And I think the future is very promising. So thank you.